There are four basic properties of a gas. The pressure, and the symbol for that is P, capital P. The volume is capital V, temperature is capital T. And the amount of gas we measure in moles, and that's given the abbreviation lowercase n, that's the variable. These four different properties are interrelated with a gas because gases, unlike liquids and solids, can change their volume. And so if we change one of these characteristics, then the others will respond. And what we call the simple gas laws describe the relationships between any two of these properties. When you get all four of them changing, it gets kind of complicated. But the simple gas laws just describe two variables at a time. So we'll look at these individually. Boyle's law. So Robert Boyle lived back in the 1600s. I give you his name and his lifespan just for interest, just for general knowledge. I will not test you on that. I will not even ask you to identify his law by his name. We need to know what the law is. We should be familiar with his name, but we're not going to be picky about which is Boyle's law and which is Charles' law, because personally, I can't keep them straight myself. So Boyle did some experiments with gases, and he used a J-shaped tube to measure the volume of a gas at different pressures. So what he did is he trapped a gas sample in this tube, and then so here he has a pressure difference, right? And then he would add mercury to the tube, which increases the pressure on this gas. We see now that the difference in heights is larger. That tells us that this gas is at a higher pressure. And then he could measure the volume of this gas. And he looked at the relationship between the volume of a gas and the pressure of a gas. And if you graph this data, we're graphing volume in liters versus pressure in millimeters of mercury, we see a curve here. And we find that as the pressure increases, the volume decreases. That's called an inverse relationship. When one goes up, the other goes down. Well, curves like this aren't all that helpful. Generally, what scientists do is we're going to try to find some arrangement where we can graph it and get a straight line. And I'll show you that in just a minute. So Boyle's law is that the volume is inversely proportional to the pressure. And that's provided you keep the temperature and the amount of gas constant. So if we graph volume versus pressure, we get a curve. But if we graph volume versus 1 over pressure, we get a straight line. And that's what this tells us, that the volume varies as 1 over the pressure. As pressure increases, volume decreases by the same factor. And so one way to express this is the pressure times the volume is equal to some constant. But the way we usually express this law is P1V1 equals P2V2. And that's one you should know. That's Boyle's law, relationship between pressure and volume of a gas. I made these graphs up because I didn't like that they didn't show you how this works in the book. So here I made up some data, and this is similar to that graph from the textbook. We see that as the pressure increases, the volume decreases. So if you take this same data and graph volume versus 1 over pressure, now you get this beautiful straight line. And we can find the equation for the line, and then we can predict what's going to happen. Like, you know, at this volume right here in the middle, what's the pressure going to be? We can have an equation for the line, and we can calculate that pretty well. Well, let's look at a molecular interpretation of Boyle's law. What's happening with the particles when this occurs, when you change the volume and the pressure is changing? So here we have a container. It's like a piston. It's got a movable lid, and you can change the volume and the pressure by putting different weights on it. So here's 1 kilogram, and we've got a volume right here of 1 liter of gas. And a pressure gauge out here is telling us that the pressure is 1 atmosphere. If we double the weight on this, we increase the pressure to 2 atmospheres, the volume drops to 1/2 liter. So we doubled this and this cut in half. That's that inverse relationship. We'll look at the particles. Now we have the same number of particles, but they're in a smaller volume. They're going to run into the walls more often. So I've told you that the gas state of students, right, is students just kind of running loose in the city, right? Let's think about kindergartners, because you guys are, you guys just sit around in chairs a lot. Kindergartners don't do that. So think about kindergartners in a room, and it's free play, right? And they're just wandering about. They're going to bump into each other. They may bump into the walls. If we take the volume of that room and cut it in half, now we've got the same number of children in a smaller space. They're going to run into each other and to the walls more often. Does that make sense? That's what happens with the gas particles. That's why the pressure goes up. Smaller container. Every time these gas particles run into a wall, it exerts a small amount of pressure. And so the number of collisions is related to the pressure. Here we have half the volume, and so we have more collisions and the pressure doubles. If you can think of gas particles, however you want to imagine them, and think about what they do, then a lot of these things you can just kind of reason out. I kind of think maybe the author of the book has been scuba diving, because he talks about scuba diving a lot in this chapter. But I think it's kind of interesting. I always wondered, why do you have to take so many classes before you can actually go out and go scuba diving? I mean, isn't it just swimming? No, it's actually much more complicated than that, and we'll see why here. So for every 10 meters that a diver goes down into the ocean, you experience approximately 1 additional atmosphere of pressure. Now that might not sound a lot, but breathing requires that we're able to create a pressure difference between the air in our lungs and the air outside. At 20 meters, you've added 2 atmospheres, so you're experiencing 3 atmospheres of pressure. Your lungs aren't strong enough. The muscles in your diaphragm are not strong enough to expand your lungs. So I didn't put it in the slides, but he also had a picture of a cartoon character. I don't know if you guys ever watched the Flintstones. But Fred and Barney would be in the lake, right? And they'd be down really far, and they just had this long tube that they're breathing through. Well, if you go down 10, 20 meters, you can't breathe through the tube, because the pressure of the water on your lungs is going to push all the air out of your lungs. So even if you have this tube of air coming down, you can't breathe because you aren't able to expand your lungs. So if you hold your breath when you're down low and you expand to the surface, the outside pressure then drops from 3 atmospheres to 1 atmosphere. And what would that cause the volume of air in your lungs to do? Expand. It would expand by a factor of 3. That's not going to feel good. So that would cause damage to your internal organs. And so that's one reason why scuba divers need to be careful to exhale frequently as they're rising. Because as you rise up, the pressure on your body is going down, and that's going to allow the oxygen, the air in your lungs to expand. Let's look at this example. A snorkeler takes a syringe filled with 16 milliliters of air from the surface, where the pressure is 1 atmosphere, to an unknown depth. The volume of the air in the syringe at this depth is 7.5 milliliters. What is the pressure at this depth? And I'm going to ignore that other question for now. So this is a Boyle's law problem. We're clued in by this Boyle's law title right here. Boyle's law is P1 V1 equals P2 V2. With gas laws, it can be very helpful to make a little table to organize the numbers because these can get a bit confusing. Here we've already got two volumes and a pressure, and so what we should do is as we go through reading the problem, find the numbers and write them down. So 16 milliliters, and we're going to have row 1 and row 2, and we need to label them. 16 milliliters is pressure, volume, temperature, or moles of gas. It's volume, right? So we're going to call this volume. So filled with 16 milliliters at the surface where the pressure is 1 atmosphere. So those two numbers go together. So this gas in the syringe, and with problems like this, sometimes it's helpful to draw a picture so that you can see in your mind what's going on. 16 milliliters of air at 1 atmosphere. And then he's diving down, and the pressure in the syringe is changing, and that causes the volume to change. So the volume changes to 7.5 milliliters. And then the question is, what's the pressure at this depth? So what I'm going to do is I'm going to call this V1, and this is P1, because it's in the P column, it's in row 1. This is V2, and I'm going to call this P2. I find this is the most straightforward way to organize my information, and so now I see that I have the correct sorts of variables for Boyle's law. P1 V1 equals P2 V2. I need to rearrange the equation. Rearrange the equation first and then put the numbers in. I'm trying to solve for P2. I'm solving for P2, and so I need to get rid of V2. So I'm going to divide that side by V2 to make it go away. If I do it to one side, I have to do it to the other side. And so we get pressure in the second circumstance is P1 V1 over V2. Be careful when you copy the 1s and 2s. It's really easy to mix them up. And I'm just going to take the numbers with their units and plug them in. So I've got 1 atmosphere, and I've got 16 milliliters, and that's divided by 7.5 milliliters. And then I do the math. 16 divided by 7.5. 2.133 is what it tells me. Look at the units. Milliliters and milliliters cancel out, and this is going to be atmospheres. How many significant figures should that number have? 2. So for our answer to what's the pressure, we're going to say 2.1 atmospheres. Any questions about that part? If the pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? So at the surface, the pressure is 1 atmosphere. So the pressure has increased by how many atmospheres? At 2.1 atmospheres? 1. 1 and a smidge, right? So the depth then is about 10 meters. So the depth is about 10 meters. Charles' law. So J.A.C. Charles, now he was later than Boyle. He lived later, 1746 to 1823. He looked at the relationship between gas volume and temperature. And he found that the gas volume is directly proportional to its absolute temperature. And we'll talk about that in a minute. So Charles' law is that volume is proportional to temperature provided you hold the pressure and the amount constant. So the volume divided by the temperature equals a constant, or the one we tend to use the most is V1 over T1 equals V2 over T2. And later I'll show you how you can derive all of these simple gas laws from the ideal gas law. What's really, really important here is that the temperature has to be in kelvins. And this is a very common error that students make on homework and exams, is they'll use degrees Celsius. It won't work. It has to be in kelvins. So here's an example of some Charles law type data, graphing volume versus temperature. Here's N equals 1 mole at the pressure of 1 atmosphere, and here are the data points. And we see that as the temperature is increased, the volume increases, and it's linear. Here's 1 atmosphere and half a mole of gas, and still it's linear. Here's 1/4 of a mole, 0.25 moles at 1 atmosphere. As we increase the temperature, the volume increases. It's linear. If we extrapolate these lines, we find that they all intersect at a temperature of minus 273.15 degrees Celsius. That's called absolute zero, and it came from experiments with gases. So if we go here, this is 0 liters in volume, this x-axis. If we go past that, that's implying negative volume of a gas. Is that possible? Can something occupy a negative volume? No, it can't. So this is the temperature where a mole of gas would occupy a volume of 0. Is it possible for a mole of gas to occupy a volume of 0? Really close to 0, but the gas molecules themselves do have volume, right? So, this is one of those things that scientists would like to argue about. Can you actually get to that? There's some people that say, no, you can't. But that's called absolute zero. When we use a Kelvin temperature scale, then we have a 0 intercept. So here's the temperature in kelvins on the bottom and in Celsius on the top. When the intercept is 0, then the equation of the line is very simple. We have y equals mx plus b, right? So y is the volume, and we have the slope. I'll just call it a constant, and x is the temperature, and this is the intercept. If the intercept is 0, then our equation is very simple, and we get volume proportional to temperature. If we use Celsius, then we have this plus something in there, and we're going to have a problem, because 0 Celsius happens right here. And so for this one, the intercept is going to be, I don't know, maybe 20. And here the intercept's going to be different, and here it's going to be different, and that makes everything complicated. But if we use the Kelvin scale, the intercept is 0. It's really important to use the Kelvin scale. Molecular view. And this is something you could try at home. Take a balloon, don't inflate it, don't blow it up too large, but you can put it in ice water and watch it shrink, and then put it in boiling water or really hot water and watch it get bigger. It's almost like magic, right? The volume of the gas in the balloon changes volume in response to the temperature. So what's going on with this? It has to do with how fast the particles are moving. Remember, temperature is a measure of the average kinetic energy of particles. At a higher temperature, the gas particles are moving faster. When they move faster, they're going to collide with the walls more frequently, and they're going to have more force when they do collide. So in order for the pressure to stay the same, the volume has to increase so that the pressure from the collisions can be the same. So we get more frequent collisions, the force is greater, and in order for the pressure to remain constant, we have to get a larger volume, and so the gas will expand. So that works in a balloon because a balloon can stretch and expand. If you do that in a sealed container, then the pressure can't change, and you won't observe Boyle's law because now you've got volume. Well, volume can't change. You're going to have temperature and pressure changing, and that's a different law. Hot air balloons. I don't know about you, but as a kid, I was like, how on earth does a hot air balloon float? Right? Okay, I understood helium balloons, right? That's fine. Helium rises. That's all good. But how can you make this ginormous balloon float and carry people when the balloon itself is open? It's got big holes in it. They put this big old burner in here, and how does that go up? Well, that giant burner heats the air. When air is heated, when the temperature goes up, the volume expands. When you have the same amount of gas in a larger volume, its density goes down. And so the density of the hot air inside the balloon is lower than the density of the cold air outside. And density, things with lower density, float in things with higher density, and so the balloon floats. And that's the same thing that happens with two-story houses in the summer. I don't know if any of you have what my kids call a stair house, but a two-story house, the upper floor is generally much warmer than the lower floor, unless you have, really good air conditioning. Why is that? Because as air warms up, it rises. Warm air rises, and so all the warm air runs up the stairs, upstairs, and the cooler air is left down below. Here's a picture of what you would see if you took that balloon and you put it in liquid nitrogen. You'll see it just shrivel and gets very, very small because liquid nitrogen's really cold. So how do we do problems like this? A gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters. If we heat the gas from 35 degrees Celsius to 155 degrees Celsius, what is its final volume in milliliters? Well, again, let's make a table. So I'm just going to make a table. I'm going to have 1 and 2, and I'm going to go through and write down numbers. So the first number I come to is 88.2 milliliters. Initial volume. Oh, cool. They even told me that was the volume. So that's the initial volume, and they're saying if we heat the gas from 35 to 155. So 35 is the initial, and 155 is the final, and that's temperature. We already have a problem. That's degrees Celsius. And they're usually going to give you temperatures in degrees Celsius because that's what the thermometers say. I haven't seen a thermometer that gives you kelvins. So you need to convert, and it's best to just convert to Kelvin right away. So plus 273.15. And we know it's 0.15, so we might as well just use that. 35 plus 273.15. So this is 308.15 Kelvin. And that just made a mess of my table, didn't it? There it is. That always scares me. Where'd all my writing go? And then do the same thing for the other temperature. Just convert it right away, because you'll forget if you decide to do it later. 155 plus 273.15. 428.15. Now, we want to keep track of significant figures, but we don't want to round until our final answer. So with this is adding. The uncertain digit is in the ones place, and so it's the 8 and the 8 here. I'm just going to keep track of that. We have one blank in our table. It's in column V in row 2, so I'm going to call that V2. And we need the law that relates volume and temperature. Now this, the way they state this in the book, this has fractions in it. And my experience is that when students deal with equations with fractions, they do dumb things. And so some of you, many of you, have no problem with algebra and rearranging things. But some of you find it a little more challenging. So I'm going to talk to those people. The rest of you will be fine. So what you should do when you have an equation like this with fractions is get rid of the fractions first and do that by cross multiplying. So I'm going to take V1, the numerator on one side times the denominator on the other side. V1 times T2, and that will equal the denominator on this side times the numerator on that side. So that equals T1 times V2. So now that equation is a lot less dangerous. I am solving for V2 here. So to get V2 by himself, I need to divide by T1, divide by T1, cancel these guys out. So you should always show your work, but sometimes you're not sure, well, what does it mean to show your work? Well, what I consider showing work is to write the rearranged equation. Some of you can do that in your head. That's awesome. But show the rearranged equation and then show it with the numbers and their units plugged in. So V1 is 88.2 milliliters. And you don't have to use a table to organize your numbers. It's just been my experience that that works the best for most students. Times T2, and we're going to divide by T1. Always put your units in there. We look at the units, we see that the units cancel out, so that's good. And then we've got 88.2 times 428.15 divided by 308.15. How many significant figures should my answer have? 3. 88.2 has 3 sig figs. 428 and 308.15 both have 3 sig figs, so my answer should have 3. So 122.5 is going to round up to 123 milliliters. That's the new volume. If we look at the question, with the simple gas laws, you can predict which direction it's going to change. So here we have a gas and we're heating it up. When we heat a gas, it gets larger. So we're expecting the volume to go up. The volume did go up. If you rearrange your equation wrong or you're not paying attention to your 1s and 2s and get your temperatures in backwards, then the volume will go down instead, and that will alert you to a problem that you need to fix. This is not the only way to solve these problems. There's a method of ratios, and if that works for you, great. You're going to get exactly the same answer, but I'm not going to teach it in class because a lot of students find it confusing. Any questions? Avogadro's law. So Avogadro, he lived in the 1800s. He was the guy to first formally state a relationship between volume of gas and amount in moles. So he found that the volume of a gas is proportional to the number of gas molecules. It's proportional to the number of particles, not to the mass of the gas. So Avogadro's law, volume is proportional to the number of moles at constant T and P. And so his law is expressed like this: V1 over N1 equals V2 over N2. Of course, we can't count gas molecules. It's more convenient to use moles. The chemist doesn't. But what we find is that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. And what's a little trippy is the identity of the gas doesn't matter. It could be any gas. The size of the particles don't matter. The size doesn't matter. The sizes of the particles don't matter. Here's a graph of Avogadro's law data. So this should make sense. As we add more gas to this container, we should see that the volume increases if the pressure and the temperature are staying the same. If we extrapolate this, we're going to see that the intercept is at 0, 0, predicting that 0 moles of gas would occupy 0 volume. And that's how it should be. A chemical reaction occurring in a cylinder equipped with a movable piston produces 0.621 moles of a gaseous product. If the cylinder contained 0.12 moles of gas before the reaction and had an initial volume of 218 liters, what was its volume after the reaction? Assume constant pressure and temperature and that the initial amount of gas completely reacts. This is like the small print. This is a situation where you might want to draw a picture. So I'm going to draw a picture up here. So here I've got, this is my gas container with the movable piston. Isn't it beautiful? Yeah. This is the piston part. It could go in or out. And this is where the gas is. So initially, what do I have in there? I've got 0.120 moles of gas in here. And there's a chemical reaction happening that's going to generate more gas, right? So it's going to produce 0.621 moles of gas. Is that the amount of gas in the cylinder at the end? No, it isn't. Because I started with 0.120. And then the reaction is producing 0.621 moles of gas. I started with some gas in there, and then gas is being added. So my final number of moles of gas is the sum of these two. So N2 is going to equal 0.120 plus 0.621, which should be 0.741 moles. Does that make sense? We don't do problems like this in 3A, but we do in 1A, because we want to see, are you able to look at this and think about it and figure it out? On an exam, there will be some straight gas law problems that are simple, and there will be some like this that require you to think about what's going on. So if I make a table, got 1 and 2. I'm starting with 0.120 moles of gas. This is N. But my final number of moles is what was originally present plus what was added. So 0.7, that's a 4. 41 moles. Now, the initial volume is 2.18 liters. That's the volume. And then we're looking for the new volume. What's going to happen? This is held at a constant pressure and temperature. Ooh. I'm looking at this and thinking, oh man, this one. So they're saying it had 0.12 moles of gas before the reaction. And there's a chemical reaction that's producing this much product. They're not specifically saying here that this gas is the reactant. If this gas is the reactant, is it still going to be there at the end? No, it's going to react. Down here, the initial amount of gas completely reacts. So then this is not what's happening. Nice. At least I caught that before we did the whole problem. So I made that harder. Nice. Because of how this is worded, then the final is 0.621 because that initial amount of gas reacted. I think this is a little too tricky for an exam question. There are other ones where it talks about adding gases that I think are really fun, but this one's not so fun. Okay, any questions about my mess that I just made? Did you follow that? What I was talking about? This means yes. This means no. Okay, I'm mostly seeing yeses. Okay, I know it's early. We need volume 1 over moles 1 equals volume 2 over N2. V1 over N1 equals V2 over N2. We're trying to find V2. So if we cross multiply, we get V1 N2 is equal to N1 V2. And then I want V2 by itself, so I'm going to divide by N1. If you need help rearranging equations, please come and talk to me, because I can give you a lot of help with that. Make sure you copy the correct equation down the right way, and then plug your numbers in. 2.18 liters times N2, 0.621 moles, divided by the initial number of moles, 120 moles. 2.18 times 0.621 divided by 0.12. How many sig figs should we report? 3. 11.3 liters. Is that a reasonable answer? We know that the amount of gas changed, right? We put more gas in. Do we expect it to get bigger or smaller? Bigger. You think about balloons. You take a balloon and it's got some air in it and you put more air in it. Does the balloon get smaller? No, it gets bigger. You put more gas in, the volume expands. Any questions? Let's do this one. This is an extra example. A scale model of a blimp rises when it's filled with helium to a volume of 55 cubic decimeters. When 1.10 mole of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of helium must be added to make it rise? Assume constant temperature and pressure. Well, what's going on here? This is one that makes a lot of students text me. What am I supposed to do here? Okay, so here's our blimp. It looks blimpy. It floats when it's got a volume of 55. So floats when V equals 55 cubic decimeters. If we put 1.1 moles of helium in the blimp, the volume is 26. Is it going to float? No. The blimp itself has some weight, has some mass. It's like a helium balloon. If you put a little bit of helium in a balloon, is it going to float if it's not inflated fairly big? No, because the buoyancy of the helium is offset by the mass of the actual latex balloon, and it won't float. You have to get enough helium in there. You have to get it large enough so it can float. And so this is saying that we have to get this blimp to 55 decimeters, cubic decimeters, before it will float. The assumption that's not stated here is that we're starting with an empty blimp, right? So we've got 1.1 moles of helium in the blimp, and this is the volume. Okay? Well, let's make a table. 1 and 2. So we're starting with a volume, well, a number of moles of 1.10. That's N. And at that number of moles, we've got 26.2 cubic decimeters. That's a unit that we don't use all that often, but it's okay. We want it to float. What does the volume need to be? 55. So we want volume of 55. And N2, is N2 going to be the answer to our question? No. That's the number of moles that need to be in the blimp when all is said and done and it starts to float. So we need that number, but it's not our final answer. But we can find what N2 is now. So V1 over N1 equals V2 over N2. Here, when you've got what you're solving for in the denominator, you have to be especially careful. Because students often solve for 1 over what they're trying to solve for, and then they don't understand why they got the answer wrong. So I want N2 by itself. Cancel those guys out. N2 equals, oh, let's write it in the same order. Not that it matters. So N1 is 1.10 moles. V2 is 55 cubic decimeters. V1 is 26.2 cubic decimeters. So the cubic decimeters cancel out. That's kind of nice. We don't have to deal with those guys anymore. We get 1.1 times 55 divided by 26.2. So N2 is equal to 2.30916 moles of helium. How many sig figs does that number have? Should it have? 3. So I'm going to underline the 0. I'm not going to round it, though, because we're not done yet. That's the moles of helium that we need in the blimp at the end. The question's asking, how many grams of helium do we have to add? Question? Well, the first thing to find out is how many moles do we need to add? If this is the final number of moles and this is the initial number of moles, how do we find out how many moles were added? Let's just subtract. So I'm going to subtract 1.10 moles. And I'm going to get 1.20916 moles added. How do we find the mass of that? We need the molar mass of helium. So we're going to multiply by 4.003 grams per mole. Sorry, I'm going to the left here. So minus 1.1 times 4.003 getting 4. Now, at this point, I can round, because this is my final answer, so I'm going to round to 3 sig figs, 4.84 grams of helium need to be added. Any questions? I think those questions like that are great on exams.